we already discussed in the previous section that if a function is continuous and you want to find the limit as x approaches some number a, then in order to find the limit, all that you have to do is a simple substitution. For example, let's say that I have the function negative 3x squared plus 2x plus 1. This is a simple continuous quadratic function. And let's pretend that we want to find the limit as x approaches any number, let's say 2. Because this is a quadratic and every quadratic is continuous in its entire domain, then I know that because of continuity, I can find the limit, I can evaluate this limit right here by doing a direct substitution. So I can continue the evaluation and say that this is equal to negative 3 times 2 squared plus 2 times 2 plus 1. I can quickly figure that out and I have an answer. Nice and simple, and immediately we are done. What happens, however, if continuity fails at a particular value of a? What happens if you are given a limit as x approaches a number a of a function, and then that function happens to be discontinuous at that value of a? We can think of an example pretty much immediately. Let's say that we have the limit as x approaches 1 of x squared minus 1 divided by x minus 1. I think that we have worked with this function already in some of the other videos. In this particular case, if I don't check for continuity at 1, if I just blindly go into substitution, I get 1 minus 1 over 1 minus 1, which is equal to 0 over 0. And when we looked at this in one of the previous videos, it was a very, very early video, could have been the introduction to limits. I said that a form like this, 0 over 0, is uninformative. It's not telling me anything. I could have a limit, I may not have a limit. If you remember, we called it an indeterminate form. And if you look back at the title right here, you're going to see exactly the same word, indeterminate. 0 over 0 is not equal to 0. 0 over 0 is not equal to 1. So this is really telling us nothing about the limit. This limit could in fact exist, or it may not exist at all. What we have to do is to find another way to figure that out. Another way would be a graph. Why not? Here you can see the graph of this function over here, x squared minus 1 divided by x minus 1. Here is the graph. So you notice that the graph is linear throughout with a removable discontinuity at 1. That is because the problem of this function happens exactly at 1. But other than that, the graph is pretty much linear. So the limit exists, right? As x approaches 1 from the left, the y values are approaching 2. And as x approaches 1 from the right, the y values are also approaching 2. So this function has a limit. In fact, we claim here that the limit as x approaches 1 of x squared minus x squared minus 1 over x minus 1 is equal to 2. So great, a graph answered the problem, right? The indeterminate case of 0 over 0 was nicely answered by a graph. But I go back to the same question. Do we always need to rely on a graph? Graphs take a while sometimes to sketch. They're not always that practical. So how can we get to the same conclusion that the limit is 2 without having to sketch a graph? And this is what typically we are going to do. Whenever we are given a limit, again, the limit as x approaches 1 of x squared minus 1 over x minus 1. And you immediately check for continuity because remember, this is the smart thing to do as I emphasized in the previous section. The first thing that you want to do is to check if the function, in this case, this function here, is continuous at 1. Because if the function is continuous at this number a, then direct substitution gives you the limit immediately. What happens if the function is not continuous? What happens if whenever you do your substitution, you get this indeterminate form, 0 over 0? If that is the case, what you are going to do is you're going to try to see if you can simplify this expression right here by using some sort of algebraic manipulation. In other words, I noticed that in the numerator, the quadratic is a difference of squares. I can go ahead and factor x squared minus 1 into x minus 1 and x plus 1. This will be divided by x minus 1. And then I noticed that these two factors will cancel out. And I am going to be left with the limit as x approaches 1 of x plus 1. So what I am finding out is that this expression right here, the original function, that original function matches perfectly with this line x plus 1, except at 1. Only at 1 is where they don't happen to be identical. Other than that, those two functions, the original one and the final expression that I have here, are identical. For every x, you're going to get the same y, except at 1. But remember that a limit, as far as a limit is concerned, the limit doesn't care about what happens at 1. The limit only cares about what happens around 1, slightly to the left of 1, slightly to the right of 1. And around 1, the one-sided limits are identical. So then that means that the limit at 1 of this function is identical to the limit at 1 of the linear function. So then, because the linear function, this one right here, is continuous at 1, then the limit of the linear function is identical to the limit of the rational function. And because of continuity, I can do substitution. I can go 1 plus 1 is equal to 2. So again, to recap, what we did was we took the original function, we did some algebraic manipulation to simplify it or re-express it as another function, in this case a line. But what is so special about this other function is that this other function is continuous at 1. So a simple substitution then gives us the value of the limit of the original function. Because again, a limit is not interested in what happens at A. It is about what happens around A. And around A, the line is identical to the original function. Only at 1, let's go back to the graph over here, only at 1 is where we have an open circle. We have a hole. We have a removable discontinuity. But around 1, if I see what happens to the left of 1 and to the right of 1, the line and the original rational function are identical. So the limits are exactly the same. Whenever you are trying to evaluate limits, you're going to get the indeterminate forms. And I think that by now we are quite familiar with 0 over 0. So imagine you're given a limit, you take a and you substitute a into the expression, you may get 0 over 0. And 0 over 0, again, says nothing about the limit of the function. The limit may or may not exist. That just means that you're going to have to do some sort of algebraic manipulation to carry on the investigation of the limit. Other forms of indeterminate cases are infinity over infinity. Just because you have infinity over infinity, remember that you cannot treat infinity as a number. You cannot say that this is equal to 1, because that means that you will be canceling infinity over infinity and therefore treating infinity as a number. And infinity is a concept, it's not a number. It is just telling us about the infinite nature of a quantity. So whenever you imagine that again, you're given a limit and you do your substitution and then you get infinity over infinity, that says nothing about the value of the limit. This is an indeterminate case. It says nothing. You're going to have to go ahead and do some sort of algebraic manipulation to figure out whether this function has a limit or not at the given value of a. Another scenario that you may have is obtaining, whenever you do your substitution, something like infinity minus infinity. A particular example of that could be the following. In this case, I have the limit as x goes to 0 of a function that consists of two components, two terms, 1 over x to the 100 minus 1 over x squared. I don't want to investigate this in a deep algebraic manner. I want us to reason through the problem just intuitively. What happens as x gets very close to 0? As x is getting very close to 0, the denominator is going to 0. The numerator is always fixed. So I'm getting something that says 1 over something very, very small. Again, something so small that is going to 0, that means that the entire ratio is getting extremely large. In other words, it's going towards infinity. Same thing over here, 1 over x squared. As x is going to 0, x squared is going to 0. The numerator is fixed at 1. So I am getting, again, 1 over something that is getting smaller and smaller and smaller. Then the result will be something that is getting larger and larger and larger. So then I conclude that this will be equal to infinity minus infinity. In other words, the first term is going to infinity as x is going to 0. And the second term is also going to infinity as x is going to 0. But then can I say that infinity minus infinity is 0? I don't think that really will be accurate. And that's because if we say that this is equal to 0, it is because we're thinking of infinity as a number. And we already said many, many, many times that infinity is a concept, it's not a real number at all. Also, in calculus, we're going to have a little bit of more respect for infinity. Yes, it is not a number, but as a concept, how large infinity is important. And by that I mean the following. Functions go to infinity as they approach a particular number, but some functions go to infinity faster than other functions. For example, if you look at 1 over x to the 100 versus 1 over x squared, 1 over x to the 100 will be going to infinity faster than 1 over x squared. And that's because the denominator, if you just focus on the denominator, x to the 100 grows faster than x squared. I mean, if you were just sketching the power functions, the denominators, imagine y sub 1 is x to the 100, and then y sub 2 is x squared. And imagine that we quickly sketch these graphs. X to the 100 will be a pretty steep graph in comparison than x squared. X squared will be more relaxed like this. This one over here, x to the 100, is going to be considerably steeper. That means that x to the 100 grows at a faster rate than x squared. So when we look at it in terms of a fraction, since the denominator is going to zero faster for x to the 100 than this one here, x squared, then the entire ratio in the first case is going to infinity faster than the second ratio. So this infinity right here, the first one, I will even highlight it in red. The first one, as infinity, is actually more powerful than the second one right here. So then, if you want to think in terms of subtraction, the first one will dominate. That means that the entire result will be another infinity. Infinity minus infinity would be infinity, because this one here would be dominating. If, on the other hand, instead of having x to the 100, you had x to the third, x cubed, then maybe those infinities would be very close together, and you may wonder if the result would become 0. Who knows? But the point is that because of these factors as to which infinity is more powerful than the other infinity, because of that, we cannot say that infinity minus infinity is 0. We can't. It may be infinity, it may be 0. We don't know. Indeterminate. We don't know. And the final indeterminate form, for now, because there are more indeterminate forms, but we're going to look at some of the other ones in later chapters. For now, the final one is going to be what happens if you have infinity times 0. In fact, there's nothing special about positive infinity. You can have positive or minus. But what happens if you get a result like this? You may be thinking that you would like to see an example. So let's consider the limit as x approaches 0 from the right of x times ln x. Ln x is the natural logarithmic function, just a logarithmic function. But as a shortcut, instead of saying the natural logarithm, you know that you can say ln x. So let's reason through this function as we did, just intuitively, as we did with this function over here. As x approaches 0 from the right, x approaches 0. Think of x as the linear function, and as x approaches 0 from the right, x is approaching 0. So I already have that the limit of x as x goes to 0 is going to be 0. What happens to ln x? If you remember the graph of the natural logarithm, in fact, of any logarithm, is an increasing function like this that approaches the y-axis asymptotically. This is 1 over here. But the point is that as x is approaching 0 from the right, look at the graph. The graph is going down, 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 all the way to negative infinity. So what I'm going to have over here is 0 times negative infinity. And it would be incorrect to say that 0 times negative infinity is going to be equal to 0. You cannot say that. It may not. It may be the case that the function that goes to negative infinity is going to go faster to negative infinity than the function that goes to 0. And if this function grows faster towards negative infinity, then the product may be something else, maybe negative infinity, who knows, but nobody says that it must be 0. If the function is going down to negative infinity very, very slow, there are some functions that go to infinity or negative infinity extremely slow. If that happens, then indeed, maybe v0 will dominate negative infinity and the product may be equal to 0. But the point is that the answer, whenever you get something like this, is indeterminate. You can't tell. The limit may or may not exist. And therefore, you're going to have to find some other algebraic, creative way to figure out what the value of the limit is. So these are the 4 types of indeterminate forms that we are going to encounter in this chapter and even the next chapter. And whenever we get these forms over here, you will not be able to make conclusions out of these 4 forms. You're going to have to find other ways to continue examining the limit. Now let's look at some examples. Let's see how do we tackle limits of functions that are discontinuous at the value of a. And a is going to change for each problem. So let's look at example 1. Find the following limits. In all of the examples that I have chosen for example number 1, all of these parts over here will be dealing with the indeterminate form of 0 over 0. Then I'm going to show you some of the other indeterminate forms and how to tackle those limits. So now let's look at 0 over 0 first. I have the limit as x approaches 1 of x to the third over x minus 1. If I try substitution, I'm going to do it right here on the side right now. If I try substitution, I'm going to get 1 minus 1 over 1 minus 1, 0 over 0. But this is something that you don't have to write it down like I did. I'm just trying to emphasize it. Checking for continuity is something that you can quickly do in your minds. Oh, if I plug in 1, I'm going to get 1 minus 1 on top, 1 minus 1 below, 0 over 0. Nope, that's not continuous at 1. So then what do I do? Remember again, getting the indeterminate form, 0 over 0, says nothing about whether the limit exists or not. We're going to have to do it algebraically, some sort of algebraic manipulation. So here I am thinking x cubed minus 1. How do we factor x cubed minus 1? So this is something that you have to remember from algebra. And in algebra, we said that if we have a to the third minus b to the third, this factors as a minus b times a squared plus ab plus b squared. So then, putting this in action, we notice that x cubed minus 1 will factor as x minus 1 times x squared plus x plus 1, all this divided by x minus 1. Notice that I haven't started substituting, so I have to keep dragging the limit notation. Now, however, I notice that I can cancel x minus 1, and it was the x minus 1 in the denominator that was causing the problem at 1, because it was x minus 1 that was going towards 0. So that was causing an issue. Same thing in the numerator. X minus 1 was causing an issue because that was giving me a 0 on top. So when you put both together, that's how we were getting 0 over 0 problem. So then, continuing now, I can now do the limit as x approaches 1 of x squared plus x plus 1. And what is really nice about this function is that this is a beautiful, continuous, quadratic function. So then I can find the limit of this function by doing a direct substitution because every quadratic function is continuous. And I know that the original function identifies with the quadratic function everywhere except when x is equal to 1. But from the point of view of the limit, I don't care about what happens at 1. I care what happens around 1. So then substituting, we're going to have 1 plus 1 plus 1, and that is going to give us 3. So this function had a limit. The limit is 3. Part B is asking us to find the limit as x approaches negative 3 of this function over this one. So one big rational function. Immediately I notice that there may be a problem at negative 3. In fact, if I try substitution, I am going to get negative 3 squared plus negative 3 minus 6 divided by negative 3 plus 3. This is going to be 9 minus 3 minus 6, which is going to be over 0. And then 9 minus 3 happens to be 6. 6 minus 6 is going to be 0 over 0. And I go, indeterminate case. Well, that says nothing about the limit. The limit may or may not exist. So I have to find another way to figure that out. And the other way, since you have a quadratic, is to try to see if the quadratic factors. And then you notice that this quadratic factors beautifully as x plus 3, and then over here times x minus 2. Then immediately I can cancel what was the problem, right? It was x plus 3 the problem. If I plug in negative 3 in the numerator, this is where I get 0. And then here, this is where I get 0. So pretty much I canceled the problem out. And now I end up getting the limit as x approaches negative 3 of x minus 2. X minus 2 is a line. Every line is continuous. So now I can perfectly evaluate this limit by doing a direct substitution. So that will be negative 3 minus 2. That is going to give me negative 5. And this is the value of that limit, negative 5. In part C, again, I can quickly try substituting 0. And I'm going to have over here 0 plus 1 is 1 minus 1 over 0. The square root of 1 is 1, and 1 minus 1 is 0 over 0. And I get immediately the indeterminate form. Again, that says nothing about my limit. So what we're going to have to try to do here is algebra. Now, I don't see a quadratic. I don't see a difference of cubes. So then factoring is not an option. But something that I can do here is to rationalize the numerator. If I want to get rid of the problem, the reason why I'm getting 0 over 0, I need to do something that will cancel. It will cancel, it must cancel this x over here. And possibly whatever is giving me 0 in the numerator as well. And I'm thinking here that rationalizing the numerator may be a way out. So if I go, okay, the conjugate of the numerator is the square root of x plus 1 over the square root of x plus 1 plus 1, that may actually be helpful. So now then, what I would have is that this is equal to the limit as x approaches 0. Now in the numerator, when I FOIL or I expand this, I'm going to get a difference of squares. So that's going to give me x plus 1 minus 1 divided by x times the square root of x plus 1 plus 1. I will not distribute this x right here, I want to leave it factored out because remember what you want is to cancel that x out. So leave it there. Don't integrate it with the rest over here. Let's continue working the numerator out. So now I'm going to have the limit as x approaches 0. And now notice over here how this 1 is going to cancel with that 1. And you're going to be left with x divided by x times the square root of x plus 1 plus 1. Now nicely, these x's will divide out and you are going to be left with the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. But now this is really hopeful because we got rid of the x's that were causing the problem. These x's were causing the indeterminacy of 0 over 0. So now that we have done a cancellation, we may want to try substitution again. And notice how this new function is continuous at 0. So let's do substitution. So this will be 1 over the square root of 0 plus 1, 1 plus 1. That means 1 over 1 plus 1, which beautifully gives us 1/2 as the value of the limit. So sometimes the algebraic manipulation that is required is multiplying by the conjugate of the numerator or the conjugate of the denominator. Part D is another limit where I don't see polynomials, so factoring will not be an option. But I do see a difference here involving radicals. So I'm thinking already of rationalizing the denominator. That means multiplying top and bottom by the conjugate. But before I engage myself in lots of algebra, let's see if I get the indeterminate. Because if I don't get the indeterminate, then a straight substitution will do the job. So let's check first before we do a lot of algebra. If I try substitution, I'm going to get 5 minus 5, 0, divided by the square root of 5 plus 4, 9, minus 3, and immediately, oh, this is not continuous. Look at this. I get 0 over 0, not continuous at 5. 0 over 0 says nothing, so I'm going to have to find another way. And I'm already thinking of rationalizing the denominator. So let's multiply top and bottom by h plus 4 plus 3 divided by the square root of h plus 4 plus 3. We're going to go ahead and carry on the simplification. In the numerator, I'm going to have just h minus 5 times the square root of h plus 4 plus 3. And remember not to try to expand this. You want to leave it in factored form because you are after canceling h minus 5. You would love to get rid of h minus 5. So leave it there in factored form. In the denominator, remember, if you multiply conjugates, you get a difference of squares. So we are going to have here h plus 4 minus 9. So then that is going to give us the limit as h approaches 5 of h minus 5 times the square root of h plus 4 plus 3. That will be divided by h minus, and minus because 4 minus 9 is 5. And if you notice, that cancels this h minus 5 and it's canceled this h minus 5 as well. So then we are going to be left with the limit as h approaches 5 of the square root of h plus 4 plus 3. Now this seems pretty continuous at 5. So let's go ahead and try the limit by doing a substitution. If we do that, we're going to have the square root of 5 plus 4, 9, plus 3. that will give us 3 plus 3, that is going to be equal to 6. And very nicely, we found the value of the limit. Example 2 is asking us to find the following limit. What is going to be different here is the indeterminacy that we're going to get. We're going to get infinity over infinity as x approaches pi over 2. So let's see exactly what happens. The way that I will demonstrate this is by looking at the graphs of tangent and secant so that you really see what happens. I mean, if you try to do a substitution, tangent of pi over 2, secant of pi over 2, you're going to have to remember that these graphs, both tangent and secant, have vertical asymptotes at pi over 2. And this is why you're getting the infinity over infinity. So let's look at the graphs. Here they are. Notice immediately that in the tangent case, as x approaches pi over 2 from the left, tangent is approaching positive infinity. For secant, as x approaches pi over 2 from the left, secant is approaching infinity. So there I have nicely infinity over infinity as x approaches pi over 2 from the left. Well, that is enough for me to realize that I cannot make any conclusions about my limit. But nonetheless, let me go ahead and see what happens on the other side of pi over 2. As x approaches pi over 2 from the right, tangent is approaching negative infinity. And as x approaches pi over 2 from the right, secant is approaching negative infinity. So then again, I have negative infinity over negative infinity, which is infinity over infinity as x approaches pi over 2 from the right. So in both cases, I get the indeterminate form. That means that, again, I can make no conclusions based on this indeterminate form. So let's do some algebra. As soon as you see tangent and secant, you have to think about re-expressing tangent in terms of sine and cosine. And the same thing with secant, re-expressing it in terms of cosine. We can write limit as x approaches pi over 2. Tangent, we know, is sine x divided by cosine of x. All this divided by 1 over the cosine of x. That's going to be equal to the limit as x approaches pi over 2 of sine x over cosine of x times cosine of x divided by 1. What is really nice now is that cosines will nicely cancel out, and we're going to have the limit as x approaches pi over 2 of sine x. Now, sine x is beautifully continuous at every x within the real numbers. So I can now do a straight substitution. I can substitute pi over 2 for x, and now I know that the sine of pi over 2 is equal to 1. So this original limit that was full of infinities and negative infinities as x approaches pi over 2, through simplification, this expression simplified to sine. So what we know is that around pi over 2, tangent over secant is exactly sine. And sine has a limit at pi over 2. So 1 ended up being the limit of the original function as well. Example 3 is asking us to find the following limit. And what is nice here is that now we're going to have this form of the indeterminate case, infinity minus infinity. So what we're going to do again is we're going to take the limit as x approaches 1 of the first term. We can think of that as a function. And then the limit of the second term, another function. Let's look at the graphs again, just as we did with tangent and secant in the previous example. So here you have the graphs. The blue graph represents 1 over x minus 1. the first term over here. And the pink graph represents 2 over x squared minus 1, the second term. And in both cases, I want you to notice what happens to the limit. As x approaches 1 from the right, both of these graphs are going towards positive infinity. So then that means that the limit becomes infinity over infinity. Then, when you look at the other side, as x approaches 1 from the left, both graphs are pointing or going towards negative infinity. So as x approaches 1 from the left, we end up getting negative infinity over negative infinity, which becomes infinity over infinity. And this is the indeterminate case. We cannot make any conclusions based on that. So now, the algebraic manipulation. We're going to go ahead, and what we are going to do is, instead of having two separate terms, why don't we get a common denominator and combine the two fractions into one single fraction? And in order to save a little bit of time so that I don't have to write limit as x goes to 1 several times as I'm doing the simplification of this expression, let me do this algebra separately. Once we simplify the expression, we're going to come back and take the limit. So this expression right here, 1 over x minus 1 minus 2 over, I'm going to even factor the denominator, x minus 1, x plus 1. And then what I want is a common denominator, so I know that I have to multiply top and bottom here by x plus 1, bracket and brackets. So moving on, this is going to be equal to x plus 1 minus 2, all this divided by x minus 1 times x plus 1, which is going to give me x minus 1 divided by x minus 1 times x plus 1. And immediately I noticed that I can cancel the x minus 1. And I'm going to have 1 over x plus 1. So then now let me go back to the actual limit. So continuing from here, this is equal. Now to give myself a little bit more space, let me continue here. This is going to be equal to the limit as x approaches 1 of 1 over x plus 1. And then I notice that 1 over x plus 1 is now continuous at 1. That means that we can do a substitution in order to get the limit of 1/2. And 1/2 becomes the value of the limit. So this function actually had a beautiful limit, 1/2. Let's look at example 4. If possible, evaluate the following limit. And it's really emphasizing if possible. What happens if I try to do a straight substitution? Let me do it here above, lightly. If I plug in 2, I'm going to have 2 squared, which is 4, minus 2, plus 5, divided by 2, minus 2. That is going to give me 4 minus 2 is 2, 2 plus 5, 7, divided by 0. And as soon as I see a non-zero over 0, I want you to remember that this is not an indeterminate form. The indeterminate forms were 0 over 0, infinity over infinity, infinity minus infinity, or 0 times infinity. These are the only indeterminate forms for now. But a non-zero over 0 is not an indeterminate form. Just like the title above says here, a non-zero over 0 is an infinite form. I am hoping that you remember from our previous discussion on vertical asymptotes that whenever you get a non-zero over a 0 at a particular value of x, that really means that we're going to have a vertical asymptote at 2. So every time, and please remember this, every time that you are evaluating a limit at some value of x, and you get a over 0 as the value of that limit, that immediately means that the answer will be plus or minus infinity. That really means that there will be a vertical asymptote at this value of x, whatever x is. In our case here, x is 2. So there will be a vertical asymptote at 2. And what you're going to have to find out is precisely the sign of infinity. Am I dealing with positive infinity? Am I dealing with negative infinity as x approaches 2? Now, how do we do that? There are two ways to do that. In order to figure out the sign of infinity, you can do it purely algebraically, or you can do it with a graph. You can always answer most limit questions with a graph. I want to show you both ways, however. So let's do it without a graph. Without a graph, I like to draw a small number line. I will position 2 right here with an open circle. I already know that because I have 7 over 0, a non-zero over 0, that means that we're going to have a vertical asymptote at x equals 2. So what we are going to do is we're going to choose test point. I'm going to choose a point to the left of 2, but very close to 2, to the left of 2. And I'm going to plug in that point into my expression, this expression right here. I'm going to plug it in. So when I do that, I'm going to plug in, let's say 1.5. Let's go to the left first. 1.5. If I plug in 1.5, 1.5, and 1.5, whatever sign I get will be the sign of infinity. So let's see exactly what happens when you plug in 1.5 into the numerator and denominator. If you plug in 1.5 here and here, you can do this with your calculator, you're going to get 5.75 if you do that. So in this case, I am going to get 5.75, and that's going to be positive. That means that the numerator is going to be positive, and the denominator, think about it, 1.5 minus 2, that's going to be negative. So then that means that we're going to get negative infinity. Why? Because you're going to have a positive number divided by a negative number is negative infinity. That is telling me that the graph is going to be approaching negative infinity as x approaches 2 from the left. And I'm going to even write that down as a conclusion here, that the limit as x approaches 2 from the left of x squared minus x plus 5 divided by x minus 2 is going to be equal to negative infinity. Then, when we go to the right, we're going to do something very similar. Now I am going to choose, let's say 2.5. Let's plug in 2.5 into x, 2.5 here, and 2.5 here. When we do the numerator for 2.5, we are going to get negative 11. No, I am lying. We are going to get 8.75. And then for the denominator, 2.5 is bigger than 2. So that denominator is going to be positive. That means that we're going to have a positive numerator, a positive denominator. That means a positive ratio. So positive infinity. The graph will be approaching positive infinity in this direction. That means that the right-hand limit the limit as x approaches 2 from the right of x squared minus x plus 5 over x minus 2 is going to be equal to positive infinity. And these are going to be your conclusions. Negative infinity for the left-hand limit, positive infinity for the right-hand limit. And I'm going to have to keep it separate because the one-sided limits have different signs for infinity. If I were to look at the sketch of the graph, this is what I would have. Right here, if you notice, this is actually the sketch of this function right here. The function that you were given, x squared minus x plus 5 over x minus 2. This is the sketch of that. And you can nicely see the infinite behavior. As x approaches 2 from the left, look at the function. It is approaching negative infinity, exactly as we concluded here on the left. And as x approaches 2 from the right, the function is going off to positive infinity, exactly as we concluded here on the right. The nice thing about this approach on the left is that I didn't have to sketch the entire graph. I only focused my attention around the vertical asymptote because this was the only problem for me, the vertical asymptote. I want you to notice that if I wanted to factor the numerator, that would have been impossible. So you couldn't have done this problem through algebra at all. If I want to factor the numerator, can you find two numbers that multiply to 5 and add to -1? Impossible. You can't. So this quadratic right here is not factorable. This is why we couldn't do any algebra. As soon as you get a non-zero over 0, you pretty much know the answer. You know that you're going to have infinity. All that you have to do is to see what happens around the vertical asymptote so that you can settle the sign of infinity. And typically you want to see what happens on the left of the vertical asymptote and then what happens on the right of the vertical asymptote. In this case, negative infinity on the left, positive infinity on the right. Sometimes you're going to have positive and positive infinity in both cases. Great. But in this case, infinity changes sign on either side of the vertical asymptote.